Alright, hi folks. So now we have to figure out, what does gravity have a use for? We know it keeps us from floating away. It even keeps our atmosphere from flying off into space. But, I mean, what good is it if these two little masses that are attracted to each other can't even go zooming together because it's so weak they can't overcome friction? So what does gravity actually do? Well, here's an example. We can think about Newton's universal law of gravitation in conjunction with his second law, F equals ma, and his third law, for every force there's an equal and opposite force. And even something as teeny tiny as this little nub of chalk I found to be able to do this, and it's getting smaller, this tiny thing, which is probably like 1 gram. And so we could think like, okay, 1 gram, you all know how to convert. So my decimal points here, 1, 2, 3. So it would be 0.001 kilograms, right? This isn't a 1, it's a K. So let's say this tiny piece of chalk, right? Tiny, tiny mass. But we know that when I let go of it, it falls toward the earth because due to gravity, everything that's not being acted upon by another force just accelerates toward the earth at 9.8 meters per second squared down toward the center of the earth. Because remember, acceleration is a vector, and so is force. Force is a vector quantity. So we're concerned about the direction of a force in the direction of an acceleration, not just the magnitude and the units. So if I've got this mass, and let's say I also know the acceleration of my little piece of chalk when I drop it is 9.8 meters per second squared, I can multiply those two numbers together, right? Because we know F equals ma. That's Newton's second law. So mass times acceleration, 0.001 kilograms. If I multiply that by 9.8, I'm essentially just moving so I would get 0.0098 kilogram meter per second squared. And you guys remember, a kilogram meter per second squared is a Newton. So I want to fit that. Newtons. So 0.0098 newtons. That's the force, right, with which the chalk is pulled down toward the center of the earth. Because, of course, every force needs a direction. So 0.0098 newtons down is the force acting on this chalk when it falls. So we can already do something with gravity because we know all these things. But here's the interesting thing. Newton's third law says that for every force, this force, there's an equal and opposite force. Chalk falls down toward the center of the earth. So what's the equal and opposite force? Earth jumps up toward chalk. The earth didn't jump. But in fact, we see that it's true. That the equal and opposite force, chalk falls down, earth comes up. That's crazy. We don't actually see that happening. How can we know that? It doesn't make any sense, does it? But if you look at it, what it's saying, for every force there's an equal and opposite force. So the force of the chalk falling down is equal to the force of the earth coming up. So let's say mass of the earth times acceleration of the earth is equal to mass of the chalk times acceleration of the chalk, which is this tiny number. Oops, that should be newtons. And I dropped my tiny piece of chalk, which I now can't even find to finish the problem. Hold on. That's not good.